Hi, what am I doing? You don't need to worry about the math over here. It's pretty elementary mensuration. So what we're after is these two containers. Now these are curd containers. This is exactly half of this in terms of the amount of curd it has, and even the price is exactly half, which in other words mean that if you buy two such containers or one of this, you get the same amount of curd at the same price, which goes on to say that any consumer must be indifferent between the choice of curd container, the small or the big, because if he has to consume 400 grams of curd, he will obviously take either this or two of this. But there is some other consideration apart from cost, or rather I should say apart from the price of these curd containers? Yes, there is. The amount of plastic used in two such containers compared to one big container, and that will be our tiebreaker. Now, why do we need to even worry about that? Because if plastic consumption in one of the cases, two such small containers or one big container is lesser, it means that it is good for the producer, for the consumer if he or she is eco-conscious, and it is also good for Mother Nature, which is like a win-win for everybody. So definitely we need to find out which of these has less plastic consumption. Now how do we do that? Now you don't need to worry about the math over here. It's pretty basic mensuration. And just to give you a bit of introduction on this, what I have assumed over here, that these guys over here are frustums, which means that the upper one has a different radius than the lower one, and you can calculate its volume and curved surface area by the standard formulae of volume and curved surface area, and that is exactly what I have done over here. So don't bother about the math over here, you just need to worry about the ratio of plastic in the big divided by the plastic into such small. Let me give you the approach what I have followed over here. So I measured the actual dimensions of these, and approximately the result is, wait for it, guess what is the result? The result is that the smaller box, two such smaller box would have more plastic, and in other words the bigger box has 20% less plastic. Now the idea here is, by measurements would not be that precise, but the results would not change by much. The result is clearly the big box is consuming less plastic. So why do we have this small box? Answer is pretty simple, because few people do not want 400 grams of curd, they want 200 grams of curd. What about them? You have to serve them as well. So for those guys we need this box. But can we make this box more efficient? Can we make this box eco-friendly? Can we make this box consume less plastic? That is our problem. And how do we tackle it? To tackle this, we need to first understand how to calculate the volume of plastic used. How do we do that? Let's understand about the boxes over here. Let me just put down the smaller one. I'll explain from the bigger one, and analysis would remain same. You imagine this box, the curd is contained inside, right? So I can just remove this bottom surface, correct? So let me just cut out this box and spread it open. I am only considering the curved surface of this frustum to calculate the plastic consumption. Why? The reason being that this surface is very similar to this surface, and if I calculate the amount of plastic consumed for the bottom base, it won't be very different from each other. the amount of plastic majorly consumed is by the curved surface. So I have done a bit of approximation here. I could have added the surface area for these guys as well, but I will leave that analysis for you if you want to do that analysis. But for my case, what I did was I just cut this guy open and imagined it like a plate. Now that plate will have a thickness and it will have a surface area. So the surface area into thickness will become the volume of the plastic used. And as I'm assuming that these two boxes have the same quality of plastic, so the thickness of plastic will remain the same. Only the curved surface area will change. So if I have to calculate the plastic consumption, I need the curved surface area only. So if I divide the curved surface area of this divided by twice of the curved surface area, why twice? Because I have two such boxes. I will get an idea that what exactly is happening with the plastic consumption, which is greater. If the ratio is greater than 1, it means the plastic consumed by the bigger is greater, and if that's less than 1, smaller plastic consumption is more. And ideally we are trying to maximize the ratio. We are trying to make it more than 1, because we have found out that as of now this guy is consuming lesser plastic, which means that the ratio is less than 1, and to be precise the ratio is around 0.8. And if we increase the ratio from 0.8 closer to 1, we have achieved our target. How do we do this? First, let's fix the dimensions of this and calculate the surface area for this, okay? And then we change the radius of the bottom, top, and if you change the radius of the bottom and top, the height will automatically change because the volume of curd must be the same. So let me just give you a bit of idea. Volume of the curd has to be the same, which means that there will be some kind of a condition, and that condition will decide the height of the small container if I choose the radius of top surface and the bottom surface iteratively. And if I form a function, I can even optimize it. But I did a bit of math, and the optimization exercise does not have a global optima, which means that I'll have to take the help of empirical exercise. Now how do we do that empirical exercise? I will note down the values of radius top, radius bottom and height and calculate the ratio. Plastic here, plastic there. So let me go to the Julia code which I have prepared to do this analysis. We begin by importing the libraries, data frames, plots, CSV. So let's just import them. Now let's just store the actual numbers. So I have calculated the plastic big actual, plastic small actual and the actual ratio, which is plastic in big upon plastic in small. Now obviously if you have followed the video so far, you have understood that these numbers is like proportional to the plastic usage. So this number is not exact plastic volume but proportional to the amount of plastic which is being used in the big box, and this is proportional to the amount of plastic used in the smaller box. That is why plastic big actual and plastic small actual, these are proportional numbers. If these two numbers are proportional to the amount of plastic used, we can divide them and find the actual ratio of the plastic used, and as expected it's 0.801, which means plastic in big is 20% less. Now let's start the actual logic of the code. So we define over here 6 arrays. Our top opt is for the radius of top of the box. Our bottom opt is radius for the bottom of the box. Now obviously this is for the smaller box. H opt is the height of the box. Again we are assuming that we are in the world of boxes which are frustums. Now we have to make the help of for loops, and then we are just using mensuration formula to calculate the implied height of the smaller box and then store it, and then we just also calculate the plastic in big, plastic in small. These are proportional numbers, and we calculate the ratio and store them. Now let's execute this also. So this gets executed pretty quickly. Now we can also store it in a data frame, because for further analysis we would need a data frame and we would need to have some kind of an idea that what's happening with the plastic ratio. So over here we are just storing it, and you can have a look at it. The R top opt has been named as radius top small. Similarly, we have a radius bottom small, then we have height small, then we have plastic in big, plastic in small, and then we have plastic ratio. Plastic ratio is stored in plastic ratio result. Now let's just make this data frame. The name of the data frame is P actual DF. Now you can see there is a display, or rather I should say a kind of a snapshot of the data frame, and it has 6 columns, and you have you already know that Julia omits few columns, so it has omitted the last column, and it has 741 rows. Now obviously we need to analyze it, we need all the columns, so we will import this into a CSV file using this command, csv.write, put the file path which you want and name of the data frame which you want to store in the file path. So I've already done this steps, I'll not do it again. So let's go to that data frame in the Google Sheets, and then just observe here that I have highlighted the condition when plastic in big is greater than plastic in small, and that is what we want, because if plastic in small is lesser than plastic in big, the ratio which we have calculated would be greater than 1, and this is desirable. This would mean that the plastic in small is lesser compared to the plastic in big, because we have fixed the plastic in big. Now if you have to just analyze this one step ahead, you can see that if you increase the radius of the bottom, the horizontal axis here denotes the radius of the bottom, the ratio of plastic in big upon plastic in small rises, and that's pretty clear with this graph. It means if you increase the radius of bottom, having met the condition that you are storing the same amount of curd and in a frustum kind of a box, you will have lesser plastic consumption. Now obviously I don't want to do analysis of it statistically, we just wanted to explore the mathematical possibility. So there is a mathematical possibility of saving plastics, so that is why this analysis was needed. And just to brief you over here what's happening in this chart, if you increase the radius of the bottom of the small box, the plastic in big upon plastic in small rises, and as the plastic in big is fixed, plastic in small has to fall, which means you have to have a very high radius of bottom small, and obviously you will follow the condition that the radius of top small has to be greater, which means it's a kind of a normal frustum where the upper radius is greater than the lower radius, and also height can be calculated using the idea that the volume is fixed, because the amount of curd has to be 200 gram exactly. So if I fix the amount of curd, we can calculate the height as well. So here you have your results. These highlighted guys over here, the radius of top small, radius of bottom small, height of small, plastic in big, plastic in small, gives you the idea that what should be the dimensions of the small container or small box, so that you have lesser consumption of plastic in the small container. Obviously now numbers would change when we measure things exactly. I have made the help of approximation in the measurement of the container dimensions, but yes, the mathematical analysis, the programming would not change, only the measurement precision will differ. The rigor will remain the same.
If you like this video, do give it a thumbs up and do not forget to subscribe, because in this channel you will find content related to maths, economics, finance, data science and everything else related to knowledge.